sort of slightly more technical introduction to the dualizing sheaf. Omega x, and what it means for x to be Gorenstein. So I've been talking about this non-singular surface S and maybe some curve D on it. And then I'm looking at Ks plus D and asking about its base locus in terms of D. And we get to this place where I have MP times OS of Ks plus D. And we say we blow this up, blow up, to make this a locally free sheaf. Right. So I'm trying to handle an H1 there, and you know this strategy going back to probably before Bombieri, but at least Bombieri, is we don't like sheaves that are not locally free, so we blow it up a bit and make it a H1. So now I'm going to scrap this. I'm saying I want to think of this as MP times a sheaf OS of Ks plus D, and this is going to restrict down to omega D. So you know, you should think of this as being like KD, but I need to explain what this means. So this is MP times OD, and then apply, and there's an H1 here, corresponds directly to HOM something. Right. So in other words, so there's this is a sort of technical sidestep, which says, well, actually, we don't need to blow up this point. We can understand this point, singular point, in its own terms. And what we have to do is understand that in the middle of this proof there was a duality. And we can also think of this duality as being in terms of, not in terms of H1, but in terms of X1. Right? And so I want to start explaining what all these ideas are. So you know, first of all, I've got this. So if D is you know, some NiCi on a surface S, then we have, you know, the OD. You know, we have plenty of practice working with this. Right, and then sometimes we're going to also be interested in OD of Ks plus D. Right, so this is I go up to the surface. I go to the D is contained in S. Right, I'm thinking of here. This is something. This is sheaves on. This is differentials on S with poles along D, and then I restrict that to D. Right, and this guy is omega D, and so this is the dualizing sheaf of the scheme D. Right, and H1 of stuff on C on D, H1 of D of some sheaf F is dual to HOM of F into omega D. Okay, so this is just a slightly more direct way of doing this than blowing up. Of course, here we're restricting down to curves and so on, so there's also some technical steps in here. But I want to explain what all of this stuff is. Right? And then, if X is a surface, so S goes to X, if this is the canonical model of S, it means contract, i.e. contract all the minus 2 curves to point to Duval singularities. Right. Then, this X has this property which is called Gorenstein. So if C in X now is a Cartier divisor, then also omega C, then also C is Gorenstein. And omega C is x1 of OC into omega C, and this is omega X, and this is the same thing as omega X of C restricted to C. So, I want to explain all this and sort of make it. These are ideas which, in the current cases for curves and surfaces, are really very, very concrete and very simple, and it is just technically the best way of approaching these problems. So that I'm working partly from this paper, which I'll show you. It's Catanese, Franciosi, Horikawa, and Reid, called Embedding. So, we start off with some of this waffle, talking about dualizing sheaves and so on, and then at the bottom of page 2 on the paper, we state the strongest form of Bombieri's embedding theorems. So it's just I'm saying all kinds of, technically tricky things that maybe you've not had occasion to understand in the past. But this is really all stuff which you can eventually get used to, and it's technically the best way of handling several of these issues. Okay, so I haven't sort of thought about exactly how to present all of this. So a general definition. So this is for a local ring. So a local ring is called A, M, or point of a scheme. So this is called P and X, or OX, P, M, P. So this is, Gorenstein is the statement that first it's Kern-Macaulay, which I have to explain. Plus omega X locally isomorphic to OX. So this is I mean locally. Okay, so OX is of course the structure sheaf, saying that something is isomorphic to omega X. Isomorphic to OX means that it's locally free. So this means that this means the canonical class. The canonical divisor is Cartier. Okay, so I'm sure that several people in the audience here know perfectly well what Kern-Macaulay is, and I'm only going to confuse them. but let me explain it in my own words. So the idea is, so Kern-Macaulay says I can cut down. This means I can cut down x to zero-dimensional by a regular sequence. Okay, so you know, I'm going to use this language. You know, if you want to think of the commutative algebra, then x is just spec of A, and m is the maximal ideal. M is the maximal ideal of a point there, right? And so what I mean by this is, here I've got x, Ox. So I'm going to take an element S in Ox, OXP. Sorry, I'm going to take an element S in MP. Now this is local at P, right? And I want this guy to be a non-zero divisor. Right, so in this case I define x1 in x to be given by s equals 0. And then, you know, the fact that this is a non-zero divisor means Ox maps into S by Ox maps to Ox1. Right, it means there's a principal ideal and then this is just the quotient by principal ideal. Okay, so it's obvious we can just do this, and I cut by one element, and I cut by another element, and I continue doing this. Okay, so it's obvious I can always do this. Okay, wrong. So example. So you know, this, if you've ever done a course on commutative algebra that includes anything about primary decomposition, then you will have seen this example, because it's a unique example. Right? I take the affine plane A2, xy, right, and inside it I take this little thing here, which is x squared xy. Right? This is the intersection of 2L, the y-axis. Sorry, I'm drawing it the wrong way. The 2L with xy equals 0. Okay, and so what this is outside the origin here I've got xy equals 0, so it's reduced, and then here it's not there at all because I've got x squared equals 0. However, at the origin there's still this little piece of infinitesimal mess sticking out. So local ring is k of xy divided by x squared xy, yes, localized at the origin. And inside here I have this little element x, right? So x is not 0. X starts off by being an element in this ring, and I've reduced to modulo this ideal. X does not belong to this ideal, so x is not 0. But you know, f times x equals 0 for all f in the maximal ideal. Right? Because anything in the maximal ideal is a combination of x and y, and if I take x and I multiply them by x, I get x squared, which is in the ideal, and I multiply them by y, I get xy, which is in the ideal. Right? So there's this infinitesimal nilpotent function that lives here, which is killed by the maximal ideal. Right? So because of x, every element of M is a 0 divisor. Right? And so this is not Kern-Macaulay. Okay, so I want to cut x down to 0-dimensional. And so, you know, if x starts off by being n-dimensional, then this is n-1 dimensional. I want to continue going. So the general definition is I can find a regular sequence of length n equals to the dimension, and then I want to, so in general, dimension x equals n, and then I want S1, S2, S3, Sn, a regular sequence, and I want that, so regular sequence, so I want that, this is the definition of regular sequence. It means that Si is a non-zero divisor of OX divided by S1, let's say Si plus 1, Si. Right. And that's eventually when I get down to OX divided by S1 down to Sn, this is, you know, this is Xn, this is O of Xn. I want this to be an Artinian ring, Artinian local ring. Right, so Artinian, saying this is an Artinian ring, it means it's finite dimensional, it's a K-algebra, finite dimensional K-algebra, or it means that S1 up to Sn contains, by the Null-Stern-Satz, this means that this contains some power of the maximal ideal. Right, so these, or, you know, zero-dimensional. These are the same, these are equivalent conditions. Right? So this is a geometric thing to do. I've got a big fat variety here. I want to cut him once, decrease the dimension, and then I cut him a second time, cut him a third time, until I get down to 0 dimensions. Right? But I want to do this by a regular sequence. So another example. So you know, you better know these examples. So you know, the thing I'm telling you is some kind of obscure knowledge that comes from commutative algebra. Right? Most of you have seen these words before in any case. Right? What I'm trying to tell you is that, you know, on the one hand you learn the definition. The definition is not especially, you know, easy to visualize and so on, but most varieties that we are ever going to meet are will be Kern-Macaulay. So in other words, this condition usually holds. So, you know, I can make a counterexample here, and I'm going to give you a second counterexample. But so there's another important point here, which is that essentially the definition here, to be a regular sequence, does not depend on the particular elements S1 up to Sn. So in other words, if it holds for one particular element, then it holds for basically any general set of n elements in the maximal ideal of the local ring. So, you know, when you do a polynomial ring, you write down k of x1 up to xn. If you ask, you know, x1 is a non-zero divisor, of course, because it's an integral domain. Divide by x1, and you get polynomial ring in x2 up to xn. That's still an integral domain, and so on. You just continue going. So x1 up to xn is a regular sequence in the polynomial ring. But if you take n basically arbitrary elements of the maximal ideal in the polynomial ring, there will still be a regular sequence. So it's almost once you have this for one regular sequence, you have it for all. So let me give the second counterexample. This is due to Mr. Macaulay, I think, who was an English school teacher about 1910. Anyway, the example is this. So I want to take C2 with coordinates uv, and I want to map this into C4 by u to the fourth u cubed v uv cubed v to the fourth. Right? So call these guys, say, T0, T1, T3, and T4. Right? And I have not written down there T2, which is u squared v squared. Okay, so the thing I'm doing here is, it's the picture's two-dimensional. I'm taking this two-dimensional thing and I'm sort of mapping him in like this. So I've written down essentially all the monomials of degree 4, except I've forgotten one of them. Right? And so if I'd left that one in, then I would have the ordinary cone over the twisted normal curve. This is the cone over the twisted normal curve, which has been squashed down just by one little step. Right? I've taken nice cone I've taken the nice cone including this T2, and I've just squashed them down just a little bit from 5 space to 4 space. Right, then T2 is not in. So this is X. X is spec of this guy. Is not in OX. I'm thinking of this OX, and I'm thinking of the origin in OX as the point. Okay, this guy T is not in OX. On the other hand, T2 is in the rational functions on X. This T2 is certainly easy to express as a rational function of these guys. For example, he's a product T0 T1 divided by product T0 T3 divided by T1 squared or something like that. And also, if I do Ti times T2, this is in OX for all I. Right? So this guy T2 is not in there. He's not in the ring. Right? But if I multiply by any of these Ti's, then he is in the ring. Right? So it's a bit like that little piece of fluff here. It's a bit like this guy here, which is not 0, but if I multiply by him by anything in the maximal ideal, here's 0. So the conclusion is that if f is in the maximal ideal of xp, any element, then f times this T2 is in OXP divided by f. Right, and he's not 0, but the maximal ideal of this OXP divided by f. So sorry. Let me take any element and let me write down x1 for x divided by x intersect f equals 0. Right, so OX1 is OX divided by f. Right, then inside there I've got f times T2. And this is not 0, but m times ft2 equals 0, because this is f times mt2. Okay, let's try and understand this clearly. So, I have this variety like this. Now, this is the cone over the quartic rational curve, right? And then I have this x primed, right? Sorry, this is x. This is the normalization of x, right? There's just this one function, t2 here, function there. This t2 is not in OX, right? But maximal ideal times t2 is in OX. Right, I have this rational function there, which is, you know, he's not a regular function on OX. On the other hand, he's an element of the function of the field of fractions, and multiplied by anything in the maximal ideal, he is in OX. Right, so I take something in the maximal ideal and I cut x by this f. So I'm taking some hypersurface and I'm cutting. This is x1, which is f equals 0. Right, so the local ring of this variety x1 is just the original OX divided by the f. Right? Now there's this element f times t2 which is in here, right? Because f times anything in the maximal ideal times t2 is in here. Right? So f times t2 is in there, and he's not 0. He's not 0 because t2 is not in there, and so this guy here is not a multiple of f. However, if I multiply him by anything in the maximal ideal, this is m times f times t2. Right? And this is the same thing as f times something in m times t2. And this element is in there, is in OX. Right? And so therefore, after cutting by f equals 0, I have a new element, an element. This is f times t2, which is killed by the maximal ideal. Now, a non-zero element killed by m, and therefore no regular elements. Okay, so, you know, the example is simple enough. The phenomenon itself is sort of pretty obscure, pretty strange. Anyway, the thing to remember is that a normal surface is Cohn-Macaulay, and you know, the cone over an irregular surface is not, for basically the same reason. Right? I take an irregular surface. I take, for example, an abelian surface, an abelian variety, or a ruled surface of positive genus. Then when I cut it, I'll have one of these varieties like this, which is not normal. Okay, so you know the kind of pieces of reassurance I give you is that most in other words, Cohn-Macaulay is not automatic, but most commonly occurring are Cohn-Macaulay. And it doesn't depend on the order. It doesn't depend on the choice of xi, of si. So in other words, you know, if the thing is Cohn-Macaulay, if there exists one of these, but once there exists one, then basically any sequence I choose like this, which actually cuts down to 0 dimension, will automatically be a regular sequence. i.e., if there exists a regular sequence, then any sequence t1 up to tn that cuts the dimension down to 0 is automatically regular. Right. So, you know, all the time in algebraic geometry we like to work with varieties that are complete intersections. And if it's a complete intersection, it's it's a quotient, it's obtained from a bigger variety by cutting by a regular sequence. Okay, so now I want to say, so, you know, from now on I'm just going to say Kern-Macaulay. So, you know, yes?
The observation you make there implied that the canonical ring of irregular surface is not Kern-Macaulay?
It's never.
It's never.
Never. It's, you know, it's never Kern-Macaulay. You know, I don't understand irregular surfaces for that reason. Okay, so I wanted to make one other kind of reassuring observation, but I've forgotten what it was. So, you know, at the beginning of a course of algebraic geometry, you learn the definition of coherent cohomology groups. And, you know, basically they're abstract and difficult, and they're, you know, you work with them by fitting them in exact sequences, but you don't actually understand what they are. Right? If somebody tells you, right, here is a secret method, a magic method, which says that all of these groups are zero, then you're very happy. Right? Because you still don't understand the definition, but you know at least the thing that you're defining is zero. Right? And Kern-Macaulay is exactly like that. There are all kinds of local cohomology groups associated with varieties and so on, and if it's Kern-Macaulay, then it doesn't have any of these. So, you know, you should be very glad to assume that a variety is Kern-Macaulay, or to hear somebody else tell you that a variety is Kern-Macaulay, because it means that lots and lots of horrid things that you don't understand very well are actually all zero. Okay, so now I'm going to say Gorenstein. And I'm going to give one or two examples, especially examples. So, you know, what I want is, so x, and, you know, a point P in x. I want that x is Kern-Macaulay, and I want that omega x is locally at P OX. So the key thing is if I have a hypersurface. So I'm going to tell you what omega x is in a while, but for the moment let's just let me just take a common sense approach to it. Omega x is something. So let's suppose that x in C3 given by f equals 0 is a surface, hypersurface, and that it's isolated singularity at the point P. Right, then I'm going to write down omega x. And the thing I'm going to write down is omega 3 of x, omega 3 of C3 with poles on x, and then restricted to x. Right, so you're supposed to think canonical, you're supposed to think the junction formula, kx plus x, restricted to x, kc3. Right, so what does this mean? So the thing you can see immediately is this is a line bundle. Right, so I'm going to call it omega x. And then I'm going to tell you outside the singular locus, then it's isomorphic to omega 2 of x. Okay, so what does this mean? So the thing I'm going to write down is dx wedge dy wedge dz divided by f. Right, so this is just a basis of this sheaf. Right, this is dx wedge. These are coordinates on the C3, so this is a basis of omega 3, and then I'm allowing poles along x. And so I've got this f here at the bottom, x is given by f equals 0, and so this is the poles along f. So this is a threefold on, it's a rational threefold on C3. It's a canonical form on C3 with poles along x, with a pole of order 1 along x. And what I'm going to do is I'm going to map this to something called the Poincaré residue of f. Right? And this is, well, I'm going to tell you it's in a roundabout way, where df by dx, df by dz is not equal to 0, send it to, go to dx wedge dy divided by df by dz. Okay, so what am I writing down here? So df by dz is not equal to 0. So this means p, this is, I'm not at the point P, I'm at a point Q in X. It's a non-singular point, right? Because the inverse function theorem, or the implicit function theorem, says if df by dz is not 0, then I can write z as a function of x and y. It's a non-singular point with local coordinates. X, y, and z equals a function of x and y. Right, this is the implicit function theorem. Yes? And so the thing I've written down here is this is a basis of omega 2x divided out by something which is a unit. Right? So this is still a basis of omega 2x. So that tells you what to do where df by dz is not 0. If df by dx or df by dy is not 0, do the same. So in other words, dx wedge dz divided by df by dy, and then maybe I need a minus 1 in there, etc. Right? Now, these three expressions, the three expressions I get are equal, because on x, df is df by dx, dx plus df by dy, dy plus df by dz, dz, this is 0. Right? So this quantity here, the Poincaré residue, this is, what is this? So he's a 2 form on x. He's rational, right? He's got a denominator, but he's a basis of omega 2x on x minus a singular locus of x. Right? So I have in mind here that, here's my x, here is some little point P that we're worried about, and let's say outside P, so therefore omega 2x is isomorphic to OX outside, away from outside P. Right, and I'm just going to define omega x to be OX extended over P with basis this residue. Residue 2x of, I'm sorry, S. This is S. Okay, so what the thing I'm doing here is I'm saying, well, you know, most people learn algebraic geometry. They learn this construction omega 2, right, or omega whatever it is. So there is this thing called the Grothendieck dualizing sheaf, or the Sayre dualizing sheaf, which is slightly more general than the top differential. So in general, if x in Pn, you know, it can be quasi projective, but I'm mostly going to use it projective. We define omega x to be equal to. So I'm going to say x is n-dimensional, and this is projective n-dimensional. I'm going to define this to be x'd n minus n of OPn OX into omega Pn. Right. So you know this is in Hartshorne chapter 3. It's in lots of other places. Right, so there are some important things to notice here. So one, it's basically not anything to do with omega n x. Right, 2. So let me assume that x is Cohen-Macaulay. Then omega x is the dualizing sheaf. Namely, for all. So what I need for this. So let me say that this is connected and purely n-dimensional. Right? X. So what I want for this is that h n of omega x is isomorphic to kx. Well, we're over a field k. Right, over the ground field. And you know, if you're proper Bourbakist, then you say that there exists an isomorphism. Right, the isomorphism is not canonical. But let me pass over the subtlety here. I have to make a choice. Right, and for all f quasi-coherent on x, h, there exists a non-degenerate pairing. So where do I want the pairing to go to? hi of f, hi of x f times times x'd. Sorry, this is straight x'd. I hope you're not too worried by these x. We'll come back to them in I'll come back to them in a minute. Xi of f omega x into hn omega x, which is k. So if f is coherent, these are finite dimensional vector spaces. Having a non-degenerate pairing means that these two vector spaces are dual to one another. Right. So if x is not Cohen-Macaulay, then you know you only get this for the top value of n or something. Let me not worry too much about it. Okay, so what do I want to do with this? So I told you that it has nothing to do with the omega nx, right? However, so the main thing this has is if x is non-singular, then omega x is isomorphic to omega nx, n direction. Right, and this process of taking x to going to the ambient space where I know the dualizing sheaf and taking x from the x into the dualizing sheaf, this is the same as the adjunction formula. So in other words, adjunction for omega n using adjunction for omega top using the residue, Poincaré residue, is the same, formally the same as adjunction for x stars. Okay, so I'm going to give an illustration of this. I'm going to tell you the case that I really want, which is how to go from a surface down to a curve. Right. So namely, suppose I've got x in y. Suppose this is codimension 1. And so I'm going to suppose that everything is Cohen-Macaulay. Macaulay and local. So this is just locally in the neighbourhood of a point, right? Then I've got an omega y, and I can discuss omega x. I'm sorry. I want to justify omega x is x1 of oy ox into omega y. Right? So, you know, I mean, there's lots of different x's here. I can compose x in the same way that I compose HOMs. So let's just understand what this is. So x1 is the derived functor of HOM. Right. So I've got some. So I've got this y. I can look at the category of coherent sheaves on y. In that category, I've got the HOM functor, HOMing anything into. I'm fixing the omega y. I'm fixing the target of the HOM. That's a certain functor. The functor has is one half exact. It's you know, exact at the left, but not exact at the right. It's an additive functor. Right? And then the x1 is just what you get at the end of that sequence where it stops being, where you have to make it into, you put a homological continuation, a long exact sequence continuing the part of the functor. Right? So I'm going to do this in general here. So I'm going to do this in this particular case. So x is in y. Right? And it's codimension 1. Right? So here's oy. Here's ox, and here is the ideal of x in y. I want to take, so this is all of these guys are coherent sheaves on y. I'm going to take HOM, this is oy blank omega y, and apply to the exact to this sequence. Okay, so I'm going to write it if I'm homing into something, then it's a contravariant functor. Okay? So what I have here is hom omega y, oy, ox into omega y. And then this maps to hom oy, omega y. Now it maps to hom ix omega y. Right, and then it continues on to x1 iy, x1 ox omega y. Right, and then it continues on to x1. Okay, so what? So now we have, this is, I've written down stuff which is all just formal. This is the definition of a derived functor. However, something very nice happens here. This guy is 0, and this guy is 0. And this guy here is just omega y. Okay, so that's the. I'm going to say that this is exactly the same as the adjunction sequence that you already know. So OX is supported on X, obviously. So it has so all of its, as far as Y is concerned, any S in OX is torsion. Right, it's killed by the ideal of X. Right, but on the other hand, omega Y is torsion free. Right, so I'm trying to map something which is completely torsion into something which is torsion free. Right, this 3. So I'm doing hom OY into omega y. Right? The omega y is already an OY module, and so I take, this is just the same thing as omega y. That will be true for any module. Right? Whereas this guy here is, so OY is projective. And so it's killed by any derived functor. Good question.
Maybe because omega y is torsion free, otherwise we don't know.
No. That would still be. It would still be the case. The place where I'm using it is the assertion that this guy will be a dualizing sheaf for X.
Okay.
Right. I mean I think writing down this, if I take omega X and take this as the definition, then this argument works through. The thing is, if your variety is not Cohen-Macaulay, then it still represents the highest dimension here. This is still true for n equals, for I equals n. It's still true that the top cohomology of any sheaf on F is the same as Homs from F into omega X. This is saying that omega X represents functor.
Okay.
Right? And then, right. And so what does this say? This says, here's omega y. It's mapping into this group here, which I can write omega y of x if I want to. Goes to omega x. Right? So this here is hom Ix into omega y. Right, so the omega y is, although y may be a completely singular sheaf, it may be non-reduced, it may be singular at its generic point, it's still the case that the sections of omega y are torsion-free. And so it makes sense to take the omega y and embed it in its sheaf of generic sections. So there's something like a function field there. And then these guys here are elements of that function field that are killed by the ideal Ix, right? So this is saying I'm allowed poles on X. So if y is generically non-singular, this is saying omega, n plus 1 of y maps to, this is the equation of X, omega n plus 1 of y with poles along X maps to omega n of X. Right, where this is the Poincaré residue. Right? So, in other words, this strange omega x that maybe you'd prefer I was not talking about, I say basically we can define it, talk about it, work with all its properties without any relation at all with Kähler differentials. Right? But on the other hand, whenever I'm working with X, a hypersurface inside Y, then I get a junction sequence, which is exactly the same as the junction sequence for Kähler differentials. So, maybe you think that working with these omegas and so on is just a kind of extra imposition. It means there's another chapter of Hartshorne that you have to read. But basically, this is a very useful thing. So, the omega x and all its manipulations, all its properties, the manipulations you have to do to it, has all the good properties of OX of KX, which is omega x. So let me put this in perspective. Suppose I take the thing I had earlier, X, a singular surface, a singular normal surface. Right, what do you have to do? So Kx, you can think of this as being, well, I'm going to take omega 1 of x, and then I'm going to take wedge 2 of omega 1 of x, and then I'm going to take the double dual of omega 1 of x. Right, so this is the reflexive hull, or the double dual. So this is OX of KX. Right, I go from whatever this sheaf is. This is a good sheaf on the non-singular locus. This is a line bundle on the locally free locus on the non-singular locus of X. I'm taking its reflexive hull and artificially making it into a reflexive sheaf. Then it's automatically a divisorial sheaf, and I call Kx the resulting divisor.
Just to kill torsion on this?
So what have I done here? Now I have omega 1x, that has possibly torsion. Right? I do wedge 2, even if I kill torsion here, the wedge 2 might still have torsion there. Right? And then I take double dual here. So double dual kills torsion and also makes the thing reflexive. So in other words, it makes it can't be extended in codimension 2. Right? So this gives, at the end of this, I get this sheaf omega x of kx. Right? So this is the same as omega x. Right? But if this were non-normal, I'd immediately be in trouble. I'm going to apply this where the variety x is an arbitrarily non-reduced curve on a surface, and I need to be able to keep control of this. So I'm trying to introduce this notion of dualizing sheaf and try to make it something that you can really work with, something you can really feel some familiarity with. It's not such a bad thing. It has all the good properties of the ordinary canonical sheaf, or the ordinary top, what's it called? Volume element, what's it called? Orientation sheaf containing the local volume elements in complex geometry. But on the other hand, it's much more general. It's defined here. It's defined essentially for an arbitrary, at least Kern-Macaulay quasi-projective variety. Okay, so I'm going to use this. So for a curve C, so this is possibly non-reduced on a surface X, possibly singular. I'm going to use this to use omega C to get a version of numerical connectedness. Right, so remember, when we're trying to prove this Bombieri embedding theorem, we can't work on the non-singular model S because of these -2 curves. We have to contract out the -2 curves. When we do that, I get a singular surface C, X. And the curve that I want to work with, maybe I'm going to take a curve in the canonical system of X, and I'm going to force it to have singularities at some point. So I can't avoid the possibility that this curve C is non-reduced and passes through the singular points of X. And I want to be able to work with it as if it were a nice curve on a non-singular surface. And I use these, so on a non-singular surface, if I've got C is NICI, then I have omega of C is O SKS plus C, restricted to CI, restricted to C, and I have lots of exact sequences involving C is A plus B. Right, and I'm going to, so you can use these in this slightly more general context in which C is, non-reduced curve on possibly singular curve X, and maybe some of these A's and B's that we write down are not, it may happen that the A and the B themselves are, not Cartier divisors on the surface X. So it can happen that the A and the B are not themselves Gorenstein, but nevertheless I can work with the C. I can get this numerical connectedness argument to work in this context. So, if you want a more precise reference to this paper of Catanese, Francesi, Horikawa, and Reid, you can have a look at it here. Okay, I'm sorry this is sort of technical, but probably if you're a beginning algebraic geometry, you need to know some of this stuff. I'm sorry? This is I call this so if X is not Cohen-Macaulay, this omega X is pre-dualizing. Right. So let me say this is useful to say. So it has it still has Hn of omega X equals K, and it still has that Hn of F is dual to Hom of F into omega X. Right, these are paired to K. So this is saying that omega X represents the functor HNF. Right? Every element of HNF comes by homming F into omega X and taking and composing that with this HN. Right? On the other hand, if I go to H, 2 of F and try to map it into X n minus 2, then maybe it'll go wrong. Right? So, if you want a proper dualizing object on X, you have to take this, not this X in a fixed dimension. You have to take the complex. You have to take the thing in the derived category. Right? So look, suppose X is a variety that has components of different dimension. Right, then you can't expect to have a duality that happens only in one dimension. Right, and so you have to have some assumption. So Gorenstein does this, or Kern-Macaulay does this. If you don't have Kern-Macaulay, then you still have a dualizing complex defined by it doesn't. No. It's strongly. So look, it represents functor. I've told you one kind of a junction theory, right? But there are lots and lots of other junction theory. There's this whole book of Hartshorne called Residues and Duality. And then somebody rewrote it 2 or 3 years ago to be a lot thinner because it's better typeset, but it's still just as complicated. So there's a whole theory of this. I'm only telling you the easy thing that I need because I'm mostly interested in Kern-Macaulay varieties. Yeah.
Surely technical. What is the importance of the normality in this construction?
Well, I want non-singular in codimension 1.
Just this to extend.
Because otherwise I don't know what a divisorial sheaf is.
You want to extend the reflexible.
Right, right. Otherwise I don't know what reflexive hull is properly.
Okay. So non-singular in codimension 1 is sufficient for this construction?
Well, yes, but if it's not Kern-Macaulay, then it won't have the right dualizing properties. You want all of these things. In practice I'm working with a quite limited set of singularities and so on. Okay? So at the moment I'm working locally. Later on we're going to do this graded, where you get, again, slightly peculiar constructions and, quite nice consequences.